Today we are very happy to have Professor Hirosi Ooguri from Caltech and Kavli IPMU, and he's going to tell us uh, about Narain to Narnia. Over to you, Hirosi.
Thank you very much. Well, thank you, Abhijit, and thank you everyone for inviting me to give this talk. And I'm very happy to be back to India. I think this is the 7th time I'm in India. Unfortunately, this time it's virtual, but it's still nice to see our friends and remind me of nice memory a couple of years ago from Mumbai. And so the title of my talk is Narain to Narnia. And actually, when I sent the title of this talk, some transcript error happened. And the mutated titles started to spread throughout the TIFR. But fortunately, my talk will work for both the original title and the mutated title. So you'll be okay, even if you are exposed to the mutated title. And so anyway, so this is the title, and this is based on the paper that just appeared, I think, few days ago on arXiv with Nathan Benjamin, Christoph Keller, and Ida Zeder. And the motivation is that there has been some funny holography going on recently. And that is the duality between quantum gravity theory, especially in low dimension, 2 dimension, 3 dimension. And that is dual to not one quantum system, but random ensemble of quantum system in 1 and 2 dimensions. And that happened to SYK model, and South Schenker Stanford had a very interesting paper. And last summer, there were a couple of papers that appeared where they talk about the duality between three-dimensional gravity, which I will explain, and average of 2-dimensional conformal field theory. And in this particular case, the Narain theory, which is a 2-dimensional CFT with toroidal target space. So this averaging that happens in the duality seems to remind us of the role of wormhole in quantum gravity. So this goes, but can you see the pointer on the screen? Good. Yeah, so I have my hand up over here.
Yeah, we can see.
It started out by I think the earlier work, but Sidney Coleman, for example, pointed out that if you have wormhole in quantum gravity, that gives rise to some random coupling. And he was trying to use that to explain the solve the cosmological constant problem. And Mardasena Mautz, after ADS CFT, pointed out that, well, it's also natural to consider wormhole in the context of ADS gravity, but that raises a puzzle about factorization of the amplitude. And so there have been lots of questions about the meaning of wormhole and what it means or not mean to the duality. Just yesterday, there was yet another interesting paper appeared by Sad, Schenker, Stanford, and Yao. Actually, I had a preview of this because Douglas Stanford gave a talk at Caltech a few weeks ago on this, and where they pointed out that you can have a situation where wormhole, but you don't have ensemble average. And you can have a situation with wormhole, with ensemble average. And they explained that in the context of SYK model, both with average in coupling constant and without average in coupling constant. So this is an interesting paper. So anyway, so these are all interesting, but this is still very puzzling in many ways. And first of all, there is no fundamental explanation so far. Maybe this new paper by South, Schenker, Stanford, and Yao explains a little bit of this on how the ensemble average emerges. So what is the rule? How does it happen? When does it happen? And does it happen in higher dimensions? That's another interesting question. So for example, there is a work by Jake McNamara and Qumran Buffer, where they made a conjecture about the baby universe. I forgot the name. There are so many conjectures. The baby universe conjectures. And then they conjecture that the dimension of the Hilbert space of the baby universe in higher dimension should be 1. And that way you can avoid having ensemble average in higher dimension with wormhole. That may be one way to resolve the puzzle in higher dimension. But maybe Saab, Schenker, Stanford, Yao work may give another way where you can have wormhole but not ensemble average. So that those are all ongoing investigation. And so the purpose of my talk is that, well, since we don't understand the derivation, maybe it helps to have more example so that we can deduce some we can find some pattern from it and deduce some principles. So that's the purpose of my talk. So I will discuss 3 examples. One is some slight generalization of this original work by Afghani, Jedi, and collaborator, and Maroni and Witten. So instead of considering toroidal target space, we'll consider orbifold target space, and that gives rise to some interesting twists to the story. And we will also discuss, I will also discuss sigma model with K3 target space and Calabi-Yau target space. So in that case, it's natural to consider sigma model and the average over moduli space of Calabi-Yau or K3, and then see what happens. And I will also
Hiroshi,
discuss, yes?
Sorry, one question.
Sure.
A priori, when you consider ADS-CFT duality in the context of any force Supriang-Mills, and you consider, let's say, duality with 2 copies of boundaries, 2 boundaries, let's say, then you would consider a classical contribution that interpolates between, right? I mean, a wormhole-like contribution that a configuration of the bulk that would interpolate between the 2 boundaries, right? So,
Right.
So what I was saying is that a priori such a thing is present, but now I guess the puzzle is how is it consistent with factorization, right? Is this how you want to look at it?
I think that's essentially the puzzle posed by Marusena and Mautz, I think. This was what they were discussing. And as far as I know, there is no complete resolution of this kind, because there are solutions in higher dimensional ADS-CFT context, and that seems to give rise to non-factorizable amplitude. But we do know that in the case of inequality, Mills, where you should have a nice holographic duality without averaging. So what's going on? Of course, it's maybe interesting question. What happens if you average, for example, overcoupling constant? But that'd be a separate question. Normal standard ADS-CFT dictionary does not require averaging. So that's a puzzle. And one resolution may be some higher dimensional generalization of what these guys did. I haven't read the whole paper, but I'm reading it.
Okay.
And maybe there must be some resolution like that, but I don't know. Yeah, but it's a puzzle. So that's why it's interesting.
Thank you.
Okay. So we go through 3 examples. I'll spend most of the time with the first example because we know more about the first example where it works, and then we see some example where it doesn't work, and then try to understand why it doesn't work and things like that. Okay. So before we get into that, let me review what Afghani, Jedi, and the collaborator, and also Maroni and Witten did. So they considered the Narain theory. And so the partial function, so the theory is characterized by a point in Narain moduli space, which is this coset space. And each point in the coset space describes even self-dual lattice of signature C and C. I'm taking C as a dimension of the target space, but it's also a central charge of the conformal field theory. And the partial function on torus worldsheet is given by the sum over momentum and winding number over lattice. So what these people pointed out was that, well, in fact, this was shown by Ziegler more than a half century ago, that you can actually average this over Narain moduli space and obtain a nice answer. And so this is an answer. And the way you prove it is that you write down differential equation. You can show that this satisfies differential equation where you can have Laplacian acting on the worldsheet moduli space, and you can have Laplacian acting on Narain moduli space. It turns out that some of them, if you add 2 Laplacian acting on it, they satisfy some eigenvalue problem. So using that, you can actually derive this equation. So it turns out that you can actually average the whole thing over Narain moduli space and write it very nicely as sum over Dedekind eta function, inverse of Dedekind eta function, which is simple function, summed over modular orbit. And then these people proposed dual gravity interpretation of the right-hand side. So the point is that where if you have this just one partition function, one eta function power to the 2c, this actually, you can think of this as partition function of Chern-Simons gauge theory in the bulk. But U1 gauge group being U1 to the C for the left, U1 to the C times U1 to the C. And it's a natural Chern-Simons gauge theory to think about because this is actually holographic dual in some sense to the free boson theory. Because each Chern-Simons, U1 Chern-Simons is dual to chiral boson. So if you have left and right, and you have C of them, okay? And this is partition function for given solid torus. But there are, for given two-dimensional torus, there are actually many ways to fill inside of the torus to make a solid tori. And in fact, there is a SL2Z over ZY's choice of this. And because what happens is that if you have two-dimensional torus, and if you try to fill inside of the torus, you have to decide which cycle of the torus is contractible in the solid torus. And there are various different choices you can make, right? You decide that you can have alpha cycle contractible, or you can have beta cycle contractible, or some linear combination of them. So this summation basically can be interpreted as summing over different way of filling inside of this two-dimensional torus. And you can show that in the case of two-dimensional torus, actually, there is only one type of three-dimensional geometry that's bounded by the torus, and that can have hyperbolic metric, and that is a solid torus. So that leads to the following conjecture. That
Sorry,
if you have,
Hiroshi,
yes,
may I ask a small question?
Yes, please.
In your first equation, that integral over the moduli space for the Narain compactification, I suppose it's done with the standard measure, right?
Yes, it's Zamolodchikov measure.
Okay.
So this theory has a natural measure, which is a Zamolodchikov measure, a metric. So you can use that to integrate. Okay.
Okay. Thank you.
Yeah. Thank you. Thank you for asking this. Okay. And so you get this answer. So the interpretation is that the left-hand side is a partial function of the averaged Narayan theory, and the right-hand side is a Chern-Simons gauge theory because each of these can be interpreted as partial function of the Chern-Simons theory on a solid torus. But you have some of them, so that means you can interpret it as coupling it to some kind of topological gravity. It doesn't have any dynamical property, but its purpose in life is just sum over hyperbolic geometries. It's namely three-dimensional metric, which allows a hyperbolic metric. So that seems to be an interpretation. If you average Chern-Simons theory, you have this. Okay. So natural question is that, well, so this is what these people did essentially, and they considered higher genus case and non-factorizable amplitude and things like that. But this was the essential observation. So natural thing is that, well, what about other conformations? There are other conformity theory with moduli space, so you can try to average them and have fun with it. And can you find some general pattern out of this investigation? So that's what we want to do. So we want to do the first example, which is averaging of orbifold conformity theory. And you can try to also average K3 or Calabi-Yau sigma model over their moduli spaces. And we also try to average over rational conformities. I'll tell you what I mean by averaging rational conformities.
Hirosi, sorry. If you plot the density of states that follows from your partition function, does that look like some sort of a sparse density up to the black hole threshold and then a continuum?
Well, actually, so this was shown, but this was looked into by Hartman, this Afghani JD paper rather carefully. And there seems to have actually interesting tail below this, but it actually goes down, I think. I don't remember exactly the shape of this, but you can easily actually Laplace transform this and obtain the density of states. And then you have this sharp cut, and then around the black hole BTZ black threshold, if I remember it correctly. But actually, I'm not sure about the interpretation of this. It has a continuum spectrum, and it's only after summing over this Euclidean geometry. And I'm not sure whether, in some sense, it has interpretation because, well, CFT side, it has interpretation, obviously. Basically, it's average of density of states. But you can see that it has a long tail towards zero because you have states. I mean, you can go to particular corner of the Narain modular space where you can have arbitrarily low-lying states, right? So therefore, average density of state would have a long tail.
I see. And is it a continuum, sort of a, there's a sharp switch at some point, right? That it's sort of like averaging the vacuum discrete spectrum up to some energy, and then after that it changes this to more like a black hole continuum. Is this right?
Well, you do see some BTZ type thing, but I don't remember exactly how it was like below the BTZ threshold. We can try to look it up, but
okay.
I do not remember.
Thank you.
Yeah, it's discussed in this paper by Afghani and collaborators.
Since we are pausing, Hirosi, may I ask a follow-up question, if you don't
Yes, please.
You know, in JT gravity, as you know very well, Stanford and Witten did this calculation early on where they showed that the degeneracy of states could not arise from a unitary Hamiltonian because they could compute it exactly, and it did not have, as you say, a discrete spectrum, but this kind of continuum. I suppose that is the same in your case, right? You can't.
Yes, that's right. That's what we were talking about. And so one of the puzzle was why you get continuum. So for example, UV theory has a continuum spectrum, but that theory does not have vacuum in the spectrum. Funny thing about some of these theory was that you have a vacuum state which are isolated, and then there is some continuum. And so then that doesn't seem to make sense because, for example, if you have non-compact direction in the target space, then the continuum should come with a volume multiplied. And but something like that can happen if you are just averaging the theory, because then the vacuum, there's a unique vacuum, so the vacuum contribution is still 1. And then you are averaging some discrete spectrum, then you can get continuum without the infinite volume factor. So that was sort of a possible explanation of this funny phenomenon, I think.
Okay, thank you.
Okay, may I go on? So let me first discuss orbifold conformal field series. So I'll spend a little more time on Z2 orbifold because this is easier to discuss. There are some new technically interesting aspects for other orbifold, but this captures the basic thing. But this is actually a very simple case. Because if you, for example, consider Z2 orbifold the partition function, it's given by the half of the original torus partition function, and then some contribution from the twisted sector. And the nice thing about this is that this is actually independent of the Narain modular, this part. So therefore, average is extremely easy because these people have already done the averaging of this part for us. And this part is modular independent, so it just comes out like that. So this is an answer for the average theory. So the question is that, can you interpret it as sum over bulk geometry? Okay. So here is a naive guess. So naive guess would have been the following. Well, so what is the orbifold? Orbifold means that you have this free boson, n free bosons, and then but it has a Z2 global symmetry because you can set x to minus x. Okay. So you gauge this global symmetry. And then that's the orbifold theory. But if you look at the ADS-CFT dictionary, then near the boundary, this x is related to the Chern-Simon gauge field A by A being equal to the derivative of x. So if you gauge x to the minus x symmetry, then in the bulk, A should be identified with minus A. Okay, so it's natural to think that the bulk dual of the orbifold theory is a Chern-Simon theory with extra Z2 gauging. Okay, so if you think about this, then the natural thing is that, well, if you have a Chern-Simon partition function on the solid torus, but if you gauge Z2 symmetry, then you should consider Z2 projection so that you only have Z2 invariant state propagating in the Chern-Simon. So natural thing is to think of solid torus partition function like this. This is after Z2 projection. But it turns out that this is not the right answer because if you sum this over all possible solid tori, it doesn't give you this answer. Okay, so we must be missing something. So what are we missing? Well, since Sandeep was a postdoc at Caltech in the 80s, he must know what John Preskill was doing. So he was saying that, well, if you have Z2 gauge symmetries, then you have to have Z2 vortices in the bulk. That's one of the hallmark of discrete group gauge symmetry. So that means that in addition to summing over geometry, you have to sum over configuration of Z2 vortices in the bulk. So for example, in particular, you should consider a situation where you have Z2 vortex going around the middle of solid torus. So if you have vortex, if you have A goes around it, you get minus A. And you can actually easily calculate the partition function with this configuration. And then you find that it gives you additional contribution like this. And then if you sum over this over SL to the images, well, you can actually prove that these two are identical. So it gives you the satisfactory answer that the average of this partition, the two orbifold partition function of a Narain moduli space is actually equal to the Chern-Simon partition function, but with extra Z2 gauging, and the sum over all possible hyperbolic structure in the bulk. For later purpose, it's actually useful to view this in a slightly different way. You can also decompose.
Sorry, Hiroshi.
Yes.
Hiroshi, may I ask a
Yes,
question?
please.
Yeah,
Yeah, sure,
it's a technical curiosity. So this additional piece here, this eta over theta 2 and so on. So these things, they look like the thing that you have after summing over gamma also, right?
Yeah, so this is invariant
Because,
under gamma. So actually summing over gamma is again trivial in that case, yes.
oh, sorry. So the second line here is not evaluated at gamma?
No, it's
Gamma tau?
evaluated at the orbit of gamma. So we sum over this over the whole thing over SL to Z over Z.
Okay.
Yeah.
And what is invariant, you said?
Invariant. What do you mean?
You said something about a piece being invariant under gamma.
Did I say that? Well, yeah. So I said that
Sorry.
this is independent of Narain moduli.
Right. So, but you see this piece there, the second piece, yeah, that piece that you are circling, that also looks like the one that is involved in the summation. So I was just wondering if there is any reason for that, because it looks the same, I thought.
Well, let me see. I'm not sure I understand what do you mean by that. So this whole partition function is of course modular invariant, if that's what you.
No. This piece, this eta over theta 2 plus eta over this thing, theta 3 and so on to the power c.
You are
So
talking
that
about
one,
this part.
yeah, that one. Now, if you write it as a sum over gamma, which you did in the next slide.
Yeah.
Okay. Yeah, here that also looks the same, right, with the gamma. So
yeah.
I mean,
so it turns out that if you sum, so what happens is that if you sum this over SL to Z over gamma, you get the same. So you get this again. So it requires this is non-trivial. This requires proof.
Okay. Yeah, that's what I was asking.
I didn't
just
explain
like
how we actually
a curious thing.
Sorry?
Okay. No, it looked like a curious thing.
I didn't explain how you do the summation, but what I can tell you is that if you sum the whole thing, then you reproduce this answer.
Okay.
Yeah. So it requires proof. Yes.
Sorry, could I ask? The eta looks, for any given way of filling out the torus, the eta looks like a sum over, like the vacuum module of the boundary Wessomino-Witten theory.
Exactly.
And now adding this new vertex is summing over some other module of the Wessomino-Witten theory.
Yes. So so that gives me a segue to the next slide.
Thank you.
But it looks like Sandeep has another question, so we can do that first.
Sorry, my question was remedial, Hirosi, which is, I know very little about 3D gravity, but when you say you sum over hyperbolic structures, at least in 2D gravity, I know that that sum is not trivial because the fundamental domain of the moduli space itself for hyperbolic structures is complicated and so on.
Right.
Isn't that the case for 3D gravity, and how do you carry out such a sum? So
well, in some sense, yes, but actually, if you fix the complex structure on the boundary, then you only have discrete choice.
Okay, I see.
So in two-dimensional Riemann surface, if you fix complex structures, then there is a unique solution to the hyperbolic metric, covariant constant curvature metric, right?
Yeah.
So it's very similar to that. So if you fix the complex structure of the boundary torus,
I see.
and then you can ask, what is the hyperbolic geometry bounded, three-dimensional hyperbolic geometry bounded by that torus? Okay. Then you have discrete choices. Okay. And these discrete choices are parameterized by this.
I see. I see. Okay,
yeah.
Very beautiful.
So this is actually very nice. So this was known to mathematicians, but this was nicely explained in the paper by Maroni and Whitten in 2007, where they consider this pure gravity business. And so that was this paper.
Thank you.
And actually, to expand on Shira's question, I'm not sure what, but I think this is what you are asking about. So if you have U1 to the C times U1 to the C Chern-Simons theory, the CFT dual has U1 to the C affine D algebra, and you have a vacuum module and you have representations. Here we are dividing by Z2, so you have a chiral algebra divided by this. And you can consider decomposing the partition function into representations. So in this case, actually, there are 4 different types of representations. You have vacuum representation, and you have some kind of twisted representation. And these are independent of moduli. And then there are some moduli-dependent representations. So in fact, it turns out that if you sum over first 4 representations corresponding to the moduli-independent representation of this chiral algebra, and then summing over this orbit, you also get this one. So this actually is another interesting way of looking at it. But so you can think of each one of them as bulk states. Okay, and you can actually interpret it that way because this is a vacuum state. So you have this vacuum propagating around it. And then you have this state, which is like a gauge field going around it, and some over this project into these 2 invariant states. And these are twisted sectors. And twisted sector is reasonable because you can have a vortex around it, and vortex gives rise to localized physical state in the bound. And then you have these vortex contributions. So you can think of this as a contribution of given solid torus, and you can actually show that this is actually identical to this one. And then you sum over a different way of summing over. Okay, am I answering Shira's question?
Yeah, yes, thank you. And just one, okay, so this Chi1, for instance, is this the module that corresponds to having a charged Wilson line in with some charge?
Yeah, so this is like twisting this by Z2 or something like that. Yeah.
I see. And yes, and does that correspond to a charged Wilson line with a particular charge or not?
Let me think. So let me see. So I think that it is not charged with respect to these U1s, right? That's what you're talking about.
Yes, that's what I meant.
These are all moduli dependent. I think charged state in this case means that state carrying winding number and momentum. And all these states have conformal dimension, which depends on the moduli. So these are all in here.
Okay, thank you.
Yeah.
Thank you.
Yeah. So all these states carries no U1 charges. These are all U1 neutral states. And you only sum over U1 neutral. In fact, there are no charged state in the solid torus because bulk theory is a pure Chern-Simons theory coupled to topological gravity. So there are no charged states. That's important. In fact, it will become important later.
Okay, so I should think of the state as charged under the Z2 in some way.
Yeah, that's a way to think about it. Okay, so these are different representations of Z2.
Yeah, thank you.
So recently, there was some paper by Alex Maroni and the collaborator, Scott Collier, etc., where they actually inserted chemical potential for these U1s, and then try to evaluate average the spectrum, also measuring their charges. But that would be different from what we are doing here, because they are considering some averaged charge distribution, which in the bulk perspective considers correspond to considering all possible way of summing of a bulk geometry. Here I'm considering some fixed bulk geometry. So that would be different.
No,
but
thank
for
you.
fixed bulk geometry, there is no charged state, I think. Okay, so that's sort of generalized what Witten and Maroni did and Afghan JD did for Narayan theory. And then we can easily generalize this for other orbifolds, Z3, Z4, Z6. But there is one important twist. That is that here we are actually averaging over entire Narayan moduli space, because even if you divide the conformal field theory by Z2, you still have the moduli space, which is the original Narayan moduli. But if you impose the orbifold, Z3 or Z4 or Z6 orbifold, then you freeze all the complex moduli of the target space. So you only average over Kela moduli. So it's kind of non-trivial. You have to reinvent what Ziegler did for not averaging over entire Narayan moduli space, but averaging only over the Kela moduli space. So, but we were able to do that. So and then after doing that, we found agreement. So I'm not going to bore you with this technicality, but there was some interesting work that we had to do to restrict ourselves to Kela moduli space.
Sorry, Hiroshi, since you brought it up, but the measure remains this natural measure.
Yeah. We consider the homological measure for the Kela moduli. So I think more interesting stories about correlation function, and the correlation function is interesting because actually there is no interesting correlation function you can consider for the original story, the story by Maroni and Witten and Afghan JD and collaborator on the Narayan modular space, because there are no interesting operators. Because the only state, only non-trivial modular independent operator is actually identity operator. And then you can have descendants of current algebra, but those are obvious. Those have obvious dual in the Baruch-Chan-Simon field. And then charged states have all modular dependent. And then there are no Baruch dual of these charged states. So in fact, so we argue that there are no interesting check you can possibly make for correlation function for this theory. But for orbifold theory, actually you can make interesting check, because you have twist operator of orbifold. So if you have local, you can have local operator around which you can have orbifold action. And for example, in Z2 case, if the target space is C dimensional, you have 2 to the C fixed point, because for each direction, you have 0 and 1/2 point, which are fixed point of Z2 transformation, Z2 reflection. So there are many fixed points. So for each fixed point, you have a twist operator where X goes around it and you get minus.
Sorry.
So this is this, yes?
Sorry, and in the bulk, would this correspond to that Wilson line and the Wilson line coming and hitting the boundary?
It's not Wilson line, but Z2 vortex hitting.
Yes, the Z2 Wilson line.
Z, yeah. So I'm explaining how this works out.
Okay, thank you.
Okay. So, but you have interesting things happening. So this was studied by in the 80s, and so you have correlation functions. And then the only constraint you have is that the sum of this epsilon has to vanish. It's some kind of charge conservation. But we can actually average this over Narayan modular space, and you find that it's actually non-zero only when these are pairwisely identified. Okay? So that's one interesting thing. And then so when they are pairwisely identified, so suppose you have epsilon fixed point, and epsilon prime fixed point, you can actually average this over Narayan modular space. And you find nice non-holomorphic Eisenstein series, where I have to explain the notation. So you have a sphere, and on the sphere, so we are considering correlation function on the sphere. And on the sphere, you have 4 points. 4 points are 0, 1, x, and infinity. And the way that people in the 80s calculated this correlation function is that to map this sphere with 4 points to a torus, because for each so if you have a sphere with 4 points, and if you have Z2 twist operator at 4 points, as you go around Z2, you get the minus sign. So it's natural to consider double cover. It's natural to consider this as each of these operators as a branch point. And then you consider double cover of a sphere. And then as you go around each of the fixed points, you come out to the other sphere. And you go around the back and you come back, right? So then you can see that you actually get a torus geometry, genus 1 geometry. And then there is a tau associated to it. So there is a natural relation between x and tau. And then you can actually average this correlation function and find that this is actually given by Eisenstein series, non-holomorphic Eisenstein series with respect to this tau, but same kind of Dedekind theta function. But actually sum is different. Previously, we were summing over SL2Z over Z. But now we are summing over gamma 2 over Z. Gamma 2 is a congruent subgroup of SL2Z, where the element, 2 by 2 matrix element, have this even and odd structure to it. So we had this result earlier in September, and it took us like half a year to figure out what this means. So of course, as Hirosi says, that this has to do with some vortex going around in the bulk. But so we wanted to understand, we wanted to have some geometric understanding of this in terms of vortex. Okay, so let me pause for just 10 seconds to let this sink into you to see how can you think of this as summing over this vortex ending on this. So it's natural to think that you have vortex coming out from this point, going in the bulk and ending over here. You have vortex coming out and ending over here, right? And then there is a natural relation between x and tau. And then it turns out the answer is sum over gamma 2 over z. Why sum over gamma 2 over z has to do with this configuration of the vortex. Okay, so this is going to be explained in the next few slides. Okay, so it turns out that this summation is actually, it can be interpreted as sum over what is called rational tangles. So I'm going to explain what rational tangles are. But these are describing configuration of these vortices. Okay, so let me first explain a little bit of notation. So I told you that when people in 80s like Dixon et al. And Buffer, Hamidi, etc., calculated this 4-point amplitude of twist operator, they mapped sphere with 4 point into torus. So this is a classic mathematics is from the 19th century, where there is a map, the relation between torus and double cover of sphere, and the relations given by this, that x is related to lambda function, which is a ratio of theta function. You can actually invert it to write it in terms of ratio of hypergeometric function. So this gives you actually a nice one-to-one map between monodromy of x around 0, 1, and infinity, and gamma 2, exactly this one. So there is actually a relation, this gamma 2, and you can therefore think of this as actually summing over monodromy. I have to explain why I divide by z. I will explain it. But basically, this, you can think of this as a monodromy of x around going 0, 1, and infinity under this map. So why is this doing this? So here is what Hirosi was suggesting. So Hirosi was saying and anticipating, I think, that so if you have this twist operator on the boundary, it's natural for the Z2 vortex to go out in the bulk. And there are actually different Z2 vortices corresponding to different choice of fixed point. This you can also see from this counting. You have 2 to the C, different kind of vortices. We explained in our paper why each vortex has to be associated to particular fixed point. But here, let's assume this is the case. So you have this going into the bulk, and then they can be tied together like that. But suppose you do the monodromy transformation. For example, if suppose x goes around y, you get this one. But then this vortex get tangled in the bulk. So it turns out that there are lots of interesting tangles. So first of all, I have to introduce notation. Tangle, in particular, what's called two tangle, is basically sphere bounding a ball, and then you have a 4 point associated to it, and then you can pairwisely connect these boundary point by a line by a curve inside of the ball. Okay, so any topological configuration of these are called tangles. So this is a trivial tangle. And the tangles that you can construct by doing monodromic transformation on the boundaries are called rational tangles. So this is actually an idea invented by John Conway. He actually tried to use this in order to actually classify knots. He wanted to have a basic building block of knots. So what he considered is that you have, when you have three-dimensional knots, you try to sort of combine this into some various smallest piece. And the smallest piece of knot he considered was this rational tangle. A rational tangle has very rich mathematics, like relation to continued fractions and things like that. But here, but there is so it looks like, given this connection, you can actually relate this as sum of rational tangles. Now you can ask, well, why we are dividing by z? The reason we are dividing by z is that even though each monodromy transformation can generate different rational tangles, but some transformation actually is trivial. So for example, if x goes around infinity, you don't get new different non-trivial rational tangles, right? You get the same trivial tangle. So that x going around infinity corresponding to z. So you have to divide by z. And then you can show that actually, you can prove rigorously that gamma 2 divided by z is actually the same as a set to this set of rational tangles.
Yeah, Hirosi, sorry.
Yeah.
Sorry. If these were normal Wilson lines in Chern-Simons theory, there would be these skein relations that would allow you to take one through the other along with reconnections. Now, in this case, since one is red and one is blue, presumably there's no possibility of reconnections, right?
Well, actually, if you do that, you change the topology for reasons I will explain.
Okay.
So you should count them differently.
Okay, thank you.
So I will explain this. So, but there is actually another puzzle, and I was hoping that somebody would ask this, which is basically what bothered us for several months, which is why we are only summing over rational tangles, if you think of this that way. Because the problem you are given was that you have a twist operator on the boundary, and it's natural that these are end point of the Z2 vortices. But then you may imagine that where this Z2 vortex goes in the bulk and do all sorts of things, and then tangled with each other. And you can, for example, tangle like this. But this is actually not the rational tangle. You can prove that you cannot get this configuration by doing monodromy transformation on this. So the question is why we are only summing over rational tangles. Okay, so we are sort of stuck for several months, and then I was happened to be reading some popular mathematics book about Thurston's work with Issei Miyake. You know, Issei Miyake is a famous Japanese fashion designer, and in the 2010 Paris collection, he decided that he's going to use Poincaré conjecture as a theme of his show in Paris, and he hired Thurston as a consultant. And he was trying to explain this, give some idea about ladies' fashion dress in terms of classification of three-dimensional topology. And basically, the idea he came up with was to consider covering, double covering, multiple covering over knots as a way of explaining various different three-dimensional topology. So that led us to actually find beautiful video discussion of by Thurston on double branch cover over tangles over knots. So it's called Knots to Narnia. So actually, I would like to show the first. So the video is for 9 minutes. It's actually very beautiful exposition of branch to double cover over knots. I highly recommend you to watch the whole thing. But let me just show the first 2 minutes of this, because that's basically the thing. Yes.
Hirosi, just 1 second, if you don't mind. If you can go back, I'm very sorry, but I didn't understand the difference. No, yeah. What exactly is the difference when you say you are not summing on the right-hand side kind of tangle.
Yeah.
What exactly is the difference between that and the left-hand side?
Okay, so this is going to be your exercise. So this one, you can show that you can get this configuration by having this X going around 1, right?
I think that's
the problem is that you cannot get this knot tangle configuration by moving X around 0, 1, and infinity.
I see.
Yeah,
Okay.
you cannot get this configuration. You can prove that this is non-rational. This is so. But yeah.
Can I just ask? So basically, these rational tangles, are they like elements of the braid group then?
It's a slightly different thing. Yeah, but it's closely related. It's very closely related to braid group.
So Hiroshi, given that Jones polynomials are obtained from Chern-Simons theory by doing these monodromies, does it make Jones polynomial a complete invariant of rational tangles?
Yeah, but these are not Wilson lines. These are vortices. So it's a slightly different observable we are talking about. Yeah.
I see. Basically, rational knots correspond to what can be obtained through monodromies of the endpoints.
That's exactly the definition that Conway used. Yes.
Okay. Thank you. Thank you.
Right. Okay. So let me show you the first 2 minutes of this Thurston's video. So can you see the video?
Yes.
Excellent. So let me prepare a little bit. So it comes with a voice, and it's essential that you can hear him. So please let me know if the voice does not come through. Okay.
I want to take you through a little exercise.
Can you hear?
Imagination that will help understand and distinguish different kinds of knots. So we're going to begin with the most ordinary knot of all, the unknot. Here's a unknot in the form of a loop of tubing. But what you may not realize right away is that this tubing has magical properties. It creates a...
Actually, Hirosi, I can't. Is there any way you could put the volume up? I can't hear it.
You cannot hear? Okay, I'm
It's
sorry.
too low. The volume is too low for me.
Oh, really? Okay, so let's see. The volume is too low? Okay. I'm very
For me, maybe some people have better speakers.
It is low, and it is on the lower side for me, but I can barely hear it. Yes.
Okay, I'm sorry that. Let me try again.
I want to take you through a little exercise of the imagination that will help.
Do you still have program?
Better.
Better.
Yeah.
Can you hear him speak?
Yes, I can hear now.
Good. Okay, so let me move the volume highest. Okay.
I want to take you through a little exercise of the imagination that will help understand and distinguish different kinds of knots. So we're going to begin with the most ordinary knot of all, the unknot. Here's a unknot in the form of a loop of tubing. But what you may not realize right away is that this tubing has magical properties. It creates a singularity in the fabric of the universe. And what it does is that if you look through the tubing, the universe you see through the tubing gradually drifts away from the universe on this side of the tubing. And over many years, its properties and its occupants change a lot. That world through the tubing is called Narnia. I can step through this magical loop. It's like a doorway into another world, the world Narnia. Here we are in Narnia. We've been exploring, we've had lots of adventures and seen many unusual and interesting sights, but we've arrived finally back at this coil, this unknotted coil. And when we look through it again, we see Earth. I'm kind of tired of being in Narnia, so I'm going to step through the coil and I'm back in Earth again. This tubing creates a two-way branching in the universe. When I go through it once, I go from Earth to Narnia. If I go through it again, I go from Narnia back to Earth. I can keep going as many times as I want, from Earth to Narnia. And it doesn't matter which direction I go through. I went from Earth to Narnia. Here I'm in Narnia, and I can step back out, and I'm in Earth again, and so forth. This is the property of the tubing. But the tubing doesn't have to be just arranged as an ordinary kind of unknotted door. What happens if you knot the tubing? Will it create the same kind of split in the universe, or will it create a different kind of split? Well, let's try and find out.
So, so that was Thurston's presentation. I hope you were able to hear that okay. And so that was beautiful presentation, and I highly recommend you watch the rest. In the reminder of this 9 minutes video, he will discuss a double branch cover of a trifold. And so see what kind of topology, three-dimensional geometry you will get by considering double branch cover of trifold. So these are beautiful. So you can ask, so you can ask the same question. So you have these various tangles, and this generate in 3-dimension double branch cover over this blue vortex and the red vortex. What kind of geometry do you get by double covering? And then it turns out that actually there is this was being investigated, and the beautiful paper by Hodgson and Rubinstein in '85. Apparently, this solves some very important problem in the knot theory. It's a famous paper, but there is a lemma in this paper where they prove that if you consider double branch cover over two tangles, then it is a solid torus if and only if the tangle is rational. Namely that you can consider any configuration of Z2 vortex, but it turns out that in order for the double branch cover to allow hyperbolic metric, the configuration has to be rational. So if you require that the bulk theory is Chern-Simons theory coupled to topological gravity, and the purpose of topological gravity is sum over hyperbolic structure, then only rational tangle configuration should be allowed. Okay, so that's a sort of natural way to understand why we should only consider rational tangle. Is that clear? No. So this gives us a very beautiful picture that if you average over the correlation function of a Narain moduli space, you get to this sum over gamma 2 over z, which you can interpret as sum over rational tangle. And the reason you sum over rational tangle is that these are configuration of Z2 vortex whose double branch cover allows hyperbolic metric. So this sort of very nicely explains why this gives this is a natural bulk dual of the correlation.
So Hirosi, I didn't understand where this requirement came from, that the double branch cover should allow a hyperbolic metric.
Yeah, because the bulk theory, we interpret bulk theory as you want to the C over Z2 Chern-Simons gauge theory coupled to topological gravity. And the purpose of life of topological gravity is to sum over all possible geometric configuration in the bulk, including configuration of the Z2 vortex. And but in such a way that you can have hyperbolic metric to it. That was our assumption. And from that assumption, we can deduce that we should only sum over rational tangle. And that agreed with Narain, the average of this correlation function.
I see. So if you didn't have a rational tangle, then you say there would be no solution to the equation of motion for the topological gravity.
Yeah, that's right. So so if you try to have a bulk geometry obtained by double branch cover of this geometry, then you cannot solve the hyperbolic metric condition. There is no solution.
Thank you.
So Hiroshi, one question. Here, the sum that you wrote down as sum over gamma belonging to z divided by gamma 2. So that is in some sense after using the Hodgson-Rubinstein theorem, right? Is there a way to write it as a sum over rational tangles? Because
Well, this is
that
sum over
manifestly has,
Sorry?
okay. I mean,
This
it
is sum
looks
over
like it
rational.
is sum over tori.
No, because this is gamma 2, not SL to Z.
Uh-huh.
So what?
I
So,
see.
yeah. So question: why this is gamma 2 and not SL to Z?
I
Is
see.
explained that way.
I see. Okay. Thank you.
Okay. So generalization to ZP overfold is interesting. So let me just briefly discuss that. And you naturally you can consider P for the branch cover over tangles. And then there is actually generalization of this statement that if you have two tangles, which is the configuration of this ZP vortex, where P is 3, 4, 6, and you should consider P for the branch cover of these tangles. And you can actually prove, and it's actually more non-trivial. It's actually, you have to use, as well as mathematicians I consulted concerned, they could prove it only using what's called Smith's conjecture, which was one of the most outstanding program in knot theory. And you can prove that P for the branch cover over two tangle is genus P-1 handle body if and only if tangle is rational. Okay. In this case, actually, there is a small issue because apparently there are some non-handle body for which you can also have hyperbolic structure. But I do not know whether those can be obtainable as P for the branch cover of any tangle. So at least those obtained from those ZP vortex configuration which are rational give rise to handle body and for which we can define hyperbolic structure.
Sorry, Hiroshi, handle body is the analog of the solid torus, I guess.
Yeah, but higher genus.
Higher genus.
Yeah.
And
so in fact, according to this work in the 80s by Dixon and collaborators, you can actually describe, so if you have a ZP overfold and if you put a twist operator, 4 point, then you get a genus P-1 surface. And its moduli is described by what is called the fake torus modulus, which is again ratio of this. And you can actually calculate a monodromy group in this case. And then it turns out that these are these groups. These are actually you can think of this as subgroup of gamma 2 over relations. And then you can consider non-holomorphic Eisenstein series and all song and dance that I did over here. Repeat this over here. Okay, so it's a very beautiful story, but actually I only have 1 more minute. So if the chairman is kind enough to give me maybe 5 minutes, I can finish my talk.
Sorry, Hirosi, I'm sorry to interrupt you when you're running out of time.
No problem.
The time limit's not serious.
You should negotiate with your chairman.
Yes, I'm sure he will be kind. Yes. I'm trying to understand the relationship between the geometry and the presence of this vortex.
Yeah.
So there's a coupling of this topological gravity to the gauge theory, I suppose. And is the coupling of the sort that it makes sure that every time you go around the vortex, you pick up a deficit angle in geometry of pi or something like that? I mean, I'm trying to understand why the vortex induces a double branched cover in geometry.
Well, so this is the same reason that you should consider genus 1 surface on the boundary. So that was sort of remember that in the case of orbifold theory, what we had was that we have this coordinate x, which maps worldsheet to the target space. And as you go around each one of these twist operator, x goes to minus x. So how do you calculate correlation function in this case? The way you think about this is that to consider double branch cover of this two-dimensional sphere branched over these 4 points, and then consider x as a function on this double branch cover. And then what happens? So you have two spheres, and you can consider sum and the difference of this. Sum is invariant under monodromy. And in fact, it has trivial partition function, so you factor that out. And the difference has exactly the property that you want to calculate. So that shows that you can actually calculate the first integral of x around with this monodromy property by considering double cover and considering field x on that double cover. That partial function, first integral of that gives the same answer. And you can repeat the same argument here too. So namely that partial function of the Chern-Simons theory in the with the monodromy property around these Z2 vortex can be calculated by going to the double branch cover. And the topological gravity goes with it somehow.
I see. So this double cover is the lift of the fact that you go twice around the Z2 orbifold, you come back to yourself.
Yes.
It's the bulk lift of that fact.
That's right.
Okay, thank you.
Yeah. Okay. So let's
sorry, could I ask one question to understand the Z2 case?
Yeah.
In this here you have this two vortices or two Z2 vortices because you're considering a 4-point function, right? And the partition function, you have just one loop, just one case, and that the sum over gamma in that case is the different ways of filling the interior of the two torus. Is that the?
Right. Yeah. So in the previous case, it was the sum over different way of filling torus. Yes.
No, with the loop also, that loop will go in different ways inside the non-trivial cycle in the interior of the torus. Is that correct?
So here the interpretation is that you are summing over different configuration of Z2 vortex, because in the case of spheres, there is only one way to fill inside of the sphere.
No, that I understand. What I'm asking, I'm asking in the case of 4-point function and the partition function without any operator insertion. In both cases, you have to sum over the different ways these loops entangle.
Yeah, but it's a different summation. It's a different summation. Here it's gamma 2 over z, and here it's gamma 2, the SL2z over z. It's a different summation.
Yeah, but there's still a sum, and that sum in that case with the loop corresponds to the way the loop can go in the interior of the filled torus in different ways. Is that correct?
Yes. That's what it is. Yes.
Okay, thank you.
Okay, and then, but then the point I was making was that there are these kind of way of vortex going.
Yeah, that was clear.
That should not be summed over somehow.
That is clear. Thank you.
Yeah.
Sorry, just to follow up on Devashish's question. So in this case here, why don't we have dynamical vortex configurations?
What are the dynamical vortex?
I mean, the way in the case of torus, when you summed over geometries, you said that, well, that is not enough. We have to add the vertices also.
Oh yeah, that's right. Oh, that's an interesting question. So why we don't have, so this needs to be explained, and we have explanation for this. So this configuration is prohibited in this case by boundary condition.
I see.
Yeah. Yeah, indeed, that's a good question. Yeah.
Thank you.
And that explains why we have this just one operator, because if you have the bulk dynamical vortex, as you said, you'd have different configurations.
Mm-hmm.
Yeah, I think that's a very good question, actually. Yeah, thank you. Okay, so I meant to actually discuss some interesting thing happening about the factorization, but I guess I'm already out of time, so -5 minutes. So let me briefly
Hiroshi, as I said in the beginning, we are flexible with time. So if you don't mind, you know, of course, you are
okay. So maybe it's okay. So this will some more quick discussion, but it's okay. So you are doing Russian style, I guess. That's yeah. Okay. So I will follow your tradition. So let me pose some questions. So this is something we don't understand. Okay. So there is so the question is about the factorizability of this amplitude. Okay. So we are considering average of partition function, average of conformal theory, and in the bulk you have various non-trivial geometry. So in particular, you have non-factorizable property. Namely, if you take product of partition function average, it's not necessarily equal to the product of average of each partition function, right? So you can calculate the difference. But then in this case, actually, you can show that only non-factorizable piece from the CFT point of view come from the contribution to the partition function from untwisted sector. Because twisted part of the partition function is independent of Narain modular. Because, for example, as I wrote over here, the partition function of Z2 orbifold is given by sum over untwisted contribution and twisted contribution. But twisted contribution is modular independent. and untwisted part depends on the Narain modular. So if you have a product of these and average that, then this twisted part is modular independent, so it should factorize trivially. So that means that non-factorizable piece should only get contribution from twisted sector, untwisted sector. But evidently that's not the case if you consider bulk dual. Because if you consider bulk dual, what kind of configuration can you consider? Of course, if you have two torus, you can fill inside of them separately by two different solid torus. You can have two solid tensor product of solid tori, which gives you sum over two torus. That would give you factorizable contribution to this. But there is a non-factorizable contribution, which is that you just consider one solid torus, and you dig out another solid torus from the middle. So then you get three-dimensional geometry bounded by two tora. Obviously, it has a hyperbolic structure because solid torus has hyperbolic structure. Okay, so that gives you non-factorizable contribution. In fact, if you do the twisted, untwisted part of the partition function, calculate the untwisted part, then it actually gives you the right answer for the non-factorizable amplitude. But this has a puzzle about factorizability because, for example, you can consider the situation where you can put the Z2 vortex in the middle of a solid torus and dig out solid torus from around it and remove Z2 vortex together with the solid torus. Then you find that this actually gives you contribution. Oh, this is the opposite. I'm sorry. So this is meant to be that this has same twisted sector, and this has twisted sector and untwisted sector. So anyway, so by putting Z2 vortex appropriately, you can have actually non-factorizable contribution even for the product of twisted and twisted, etc. But CFT calculation doesn't seem to care about it. So there seems to be some discrepancy between them. It's possible that these vortex configurations are not allowed. That's one possibility. Or they cancel, but we have not thought carefully about it. There is a related puzzle about correlation function. So for example, this is actually simpler to understand. Let's consider two-point function of twisted operator, where two-point function of twisted operator is modular independent because conformal dimension of the twisted operator is modular independent. It's like 1/8 or something like that. So therefore, if you take product of them and the average of a Narain modular space, it's factorized. Right? But evidently, there are bulk contributions which are not factorized because you can consider two-dimensional sphere and then fill that inside of that by a ball. So you can have a solid ball. And you can remove smaller solid ball from the middle. Then you can get connected geometry with two boundaries that are both spheres, right? So those are, and then you can have vortex going between these solid tori, so these boundaries, or actually ending. Those seems to give rise to non-factorizable contributions. So,
sorry, Hiroshi, even the second diagram gives non-factorizable?
Well, because there is a bulk geometry over here. So anyway, so what happens is that in addition to this, you have a product contribution. So even if this gives rise to the same number as this, you get the numerical factor wrong because this would give you additional contribution unless they cancel. So it's possible they cancel. Another possibility that this geometry doesn't have a hyperbolic geometry, hyperbolic structure. That's another possibility because this geometry is actually non-trivial. This geometry, so if you have a ball and if you just have one tangle like that, that is still a ball because it's double covering of a ball. But this one, this geometry has actually non-trivial cycle because non-trivial pi1 because you can go from here, come out here, and come back here. And so this geometry is not the trivial geometry. So it's possible that this geometry does not have a hyperbolic structure. So in that case, this is forbidden, so the puzzle is solved, right? So but we have not thought this through. So we just suppose this as a puzzle in the paper. Okay. So anyway, so there are some interesting questions about non-factorizability in this case. Okay, so I'm way out of time, but let me make some comment about more generalization. So far we have considered all before. So that was solvable. So that was good. But you can ask, well, how about K3 or Calabi-Yau? So these are more non-trivial. And so there the partition functions more interesting. So you have vacuum contribution, you have half BPS states, you have quarter BPS states, and you have non-BPS states. The quarter BPS states are totally determined by Hodge number of Calabi-Yau manifold. And you have K3. So let's first consider K3. Okay, but you can also consider Calabi-Yau too. So in the case of Calabi-Yau, in both cases, I guess you can have half BPS state, which is CC and CA primary. And you can also have quarter BPS state, which is chiral in the left mover and non-chiral on the right mover, or vice versa. And this part is essentially determined by elliptic genus, studied by, well, actually, I myself studied it in my PhD thesis, and Christoph Keller and I used that to put some constraint on the modular invariant partition function. And there are interesting story about this, like Matthew Moonshine, etc. And then there is a non-BPS state, which depends on the modular. So you can ask, well, what happens if you average this over modular space of K3 or Calabi-Yau? And can you express that as sum over bulk geometry? So we could try that. So you can ask, well, suppose you average this partition function. Can you write it as sum over the vacuum character over this modular orbit? And you can actually show that this cannot work because the left-hand side must be positive. It may have continuum, but it has to be positive because these are all positive coefficients. So even if you average over, as far as you average with positive measure, here we are averaging that over the homological measure, you should get a positive answer. But you can actually prove that this has negative coefficient. So the proof is very similar to the one that I gave with Nathan Benjamin, Xiaofeng Xiao, and Yifan Wang a couple of years ago. So we did the same exercise for pure gravity, which is dual to pure Virasoro theory. So here we are considering n equal 2 or n equal 4 superconformal character, but essentially same mechanism works. So you can actually show that it doesn't work. And actually, but you can say that, well, this is modular dependent, but these are modular independent. So very similar to the case of orbifold theory. So in the orbifold theory, we can actually, in response to Shiras's question, I explained that you can actually think of this as sum over modular independent representation of chiral algebra. So you can actually try to do the same thing. And you can actually prove that this won't work either. So it looks like there is a program in this program of averaging over modular space in K3 or Calabi-Yau. In both cases, naive generalization of orbifold and Narain theory does not seem to work. Now, finally, how about rational conformal field theory? Well, I have to tell you what I mean by averaging rational conformal field theory. Well, so let's consider minimal model, which is C less than 1, parameterized by this. I'm only considering unitary CFT. It turns out that when M is greater than or equal to 3, there are, in general, 2 or 3 inequivalent conformal field theory. You know that the conformal field theory minimal model has ADE classification. And for C equal 1/2, there is only Ising model. And the next one has only 3 critical Ising model. But for higher M, there are D series and E series. So they can have actually different conformal field theory. So you can actually sum over these 2 or 3 conformal field theory and see whether this can be interpreted as sum over vacuum characters. And in fact, it works in some cases, but there are counterexample too, where it doesn't work. By that I mean that if you do this summation, you get some negative coefficient here. Okay, so that means that this idea seems to work for some C, but not all C. And something similar was discovered recently by Sunil Mukhi and the collaborators in the SU2 Witten model. In that case, also there are some cases where you have actually some like average like this situation, and sometimes it works, sometimes it doesn't work. Okay, so I told you that we will work in a few 3 different type of conformal field theory and average them. Or before CFT, Calabi-Yau sigma model and rational CFT. And we found that for before CFT, it seems to work, even for correlation function. For K3 or Calabi-Yau sigma model, it seems that it doesn't work. There are some pathology like negative normal state. For rational CFT, it works sometimes and it doesn't work some other time. So what kind of general pattern can you derive from these three examples? We are physicists, so we are good at guessing patterns. And so but the pattern we identified was the following, that ensemble average of two-dimensional CFT has holographic interpretation only if C is equal to C critical. C critical is the following quantity. So for central charge, we know that it is appears in the Virasoro commutation relations. And it also gives you the Kavli density of state for the full partition function. But you can also ask, what is the Kavli behavior for the vacuum character? Or you can ask, what is the asymptotic number of operators in the chiral algebra? And those are given by C critical, the critical central charge. And it seems like in all these three examples, the duality works only when C is equal to C critical. But it's not a sufficient condition, but it seems like a necessary condition. Because in Narain theory, or before the theory, C is equal to C critical. And K3 or Calabi-Yau sigma model, C is actually greater than C critical and not equal to C critical. And for rational CFT, C is actually C critical. In some cases, it actually works, but there are also counterexamples. That's why we wrote only if. Okay, so that seems to be a pattern, but maybe there are more deeper things that we can find. But it seems like in order for this to work, CFT must have sufficiently large symmetry. That's what C is equal to C critical means, to organize the spectrum. And that may be why it doesn't work in higher dimension, because two-dimensional CFT has particularly large symmetry, and that's why sometimes it's solvable. Okay, so that's all I wanted to say. Thank you for your attention, and I apologize that I went way over time. Thank you.
Thank you very much, Hiroshi. Let's all unmute and thank Hiroshi for a beautiful talk.
Hi,
more questions?
I quoted you.
Yeah, well, so I had a question and a comment. So question is, what is your definition of C critical exactly? Like, is it 1 for Virasoro minimal models or less than 1?
Well, so Virasoro minimal model is actually this, because there are null states in the vacuum character.
So C critical is whatever is C for a rational theory. Is a rational theory? Does a rational theory in your language always have C equals C critical or not?
Well, I think that our idea is that C critical tells you how big the symmetry is.
Mm-hmm.
Namely that so the asymptotic density of the vacuum character count the number of independent symmetry operators, right? Because any states that appear in the vacuum characters are chiral operators.
Okay, so the C critical for SU2K Wessel-Minowitten models is just the usual central charge 3K over K plus 2.
I would think so, yes.
Okay, so in that case, our result is that in fact it always works for the identity seed, which is compatible with your conjecture. But
well, I thought that there are cases, if I read your table correctly, there are cases where it works, but there are cases when you had negative.
Yeah, that depends on it depends on the seed with which you start. That is the starting point for your Poincare series. If you take a conservative view that the starting point is always the identity character, then as per our paper, it always works. The only negativities you see in our paper are for when you start with non-identity.
Oh, okay, I see.
Now for Virasoro minimal models, that's different because there in the unitary series, you cannot find any example where it works. Here, what happens is that there are infinitely many examples where it works. There are also examples where it doesn't work. I agree.
So, but are you saying that for, yeah, do you have a proof that it's always,
oh, sorry.
So for any K?
Okay, so let me be precise. For SU2 at level K, there's an infinite set of values of K, but not all values of K.
Yeah, okay.
For which you get a positive linear combination.
Yeah, okay. So I think that was my understanding. So there are cases where it doesn't work, right?
Okay. I see that.
That was what I meant.
Yes. And okay, so therefore, from that point of view, you say that this is not a sufficient criterion, but
it's not sufficient, but seems to be necessary.
Do you think there might be some more refined criterion which is also sufficient?
I imagine. I mean, this is, we just looked at the 3 different examples and deduced this rule. So it could be that there are more refined conditions.
Mm-hmm. Thank you.
Shuhen has her hand raised, I think.
Hello, Hirosi.
Hi, good. I'm not sure. Is it good morning or good? Or it must be good evening for you.
I'm in Princeton. Yeah.
Okay.
It's in the evening. Yeah. Thank you for the very beautiful talk. I just have a very naive question. So in the bulk, you started with the U1C times U1C Chern-Simons theory coupled to topological gravity.
Yeah, that was what I understood what those people did. Yeah.
Right. And that has a Z2 global symmetry for which you gauge the Z2 global symmetry.
Right. Yeah. So this is not what you'd think in the standard ADS, because in the standard ASF, boundary global symmetry is a boundary, the bulk gauge symmetry.
Right.
But this is different.
So in the original bulk, does that mean this is a quantum gravity theory with a Z2 global symmetry?
I think so, yes. And that's allowed because I think that the statement that quantum gravity cannot have global symmetry only works for theory with black holes.
Right.
That's my understanding. And so you can have a global symmetry if you don't have black hole in the bulk. We can of course debate whether this theory has black hole or not, because you have Hawking page transition, seemingly Hawking page transition. But I do not think this theory has if I take this as a face value, there is no gravity black hole states. And indeed, I mean, Chern-Simons theory has lots of global symmetry. In addition to this, it has parity symmetry.
Yeah.
Which is not global gauge symmetry, but the global symmetry, because if we are considering parity as gauge symmetry, we should be summing over non-orientable manifold too, I think.
So the bulk doesn't have the Einstein-Hilbert term.
Right. Yeah, I think that it's mandatory that you have Einstein. Well, I think it's mandatory that you have black hole, I think, in order to, yeah. So this theory has global symmetry in the bulk, which is Z2 global symmetry. And boundary theory also have Z2 global symmetry. And the duality somehow identify global symmetry and global symmetry, not global symmetry and gauge symmetry. So if you gauge Z2 global symmetry on the boundary, we should be gauging Z2 global symmetry in the bulk too. And that was a proposal here.
I see.
Yeah,
it's a gravity theory because we are summing over geometry.
Right. We are summing over, but it's a topological gravity. So I think that's because we are only summing over hyperbolic metric. We are not having any quantum gravity fluctuation to it. Right. So it's a very sort of simple topological gravity that the Chern-Simons theory is coupled to. And I think that's why we can have global symmetry.
I see.
Onkar has a question.
Hi, Hiroshi. Thanks for the nice talk.
Nice to see you, Shuhen, by the way.
And I just had a quick question about your geometry, which you said was non-factorizable in the case of two torus boundaries.
Oh yeah. So this is a puzzle, but we are trying
Right.
to we are looking into that, trying to solve it.
Right. So my question about this non-factorizable geometry is whether it's genuinely a saddle, like what if you remove a solid torus from inside a bigger solid torus, it's not clear to me that both of these torus boundaries will have asymptotically ADS boundary conditions, right? I mean, I agree that it has hyperbolic structure, but they needn't be like asymptotic.
Okay, yeah. Well, that's an interesting point. Yes. So we have to be careful about exactly what we mean by that. So here in the original solid torus, we are assuming that for outside the torus, we have this ADS type boundary condition.
Right.
So if we remove the solid torus in the middle, we have to make sure you can do that and still maintain the hyperbolic geometry.
Yes,
I think that this question can be asked for the original paper by Maroni and Witten too. They were also discussing this kind of geometry. But I think this is a valid question because I was a little bit casual in discussing, for example, around here, whether hyperbolic metrics are allowed or not. But to be precise, we have to specify the boundary condition carefully for the hyperbolic metric. And only after that, we can actually use this theorem. So I think your point is valid. So that may be one way why this kind of things.
Right. I mean, if you don't put the asymptotic ADS boundary conditions, then there are many other like hyperbolic geometries, right?
Thank you. Yeah, I think that's a very good point. Yes.
Okay. Thank you.
Sorry, just one comment about this. I mean, with what you said, Omkar, it would mean that just having two torus boundaries would be an issue with the boundary conditions, right? So in particular, the partition function should factorize. But I thought the factorization was obstructed by at least the untwisted sector obstruction was allowed.
Right. So for Narayan theory, you have no factorizable contribution, and which seems to be consistent with this type of geometry. So in that case, it works. So in some there are cases where it works, but look like if you introduce Z2 vortex, that story gets changed somehow. So here I was just naively introducing Z2 vortex, but it's possible that if you add Z2 vortex, then hyperbolic structure is not allowed somehow. So that may be a good resolution to the problem.
Sorry, just to understand the answer to that, I mean, if you just have one torus inside another, is there a hyperbolic geometry in which both, where you become asymptotically ADS and on both sides? I didn't understand.
Yeah, so I have not followed this carefully enough because we just started to worry about it when we were writing the paper. So we had this short section on this. We want to investigate into this. But what I can say is that in the original Narayan theory, as Maroni and Witten and others studied, you do have non-factorizable contribution from CFT side because the partition function has moduli dependence. So you would expect there must be a bulk non-factorizable geometry somehow. And a natural candidate is a double solid torus.
I see, but from Unkar's comment, it's not even clear that that exists, right? Even without the vortices.
It requires proof. Yes, I agree. I
think such a saddle may not exist, but maybe off-shell configurations have to be included.
So I don't know. But it's a topological gravity, so it has to be on shell, I imagine. But Sandeep, yes.
No, I just wanted to ask, in the context of JT gravity, it was much easier to work, I mean, as you know very well, in the first order formalism directly to establish these configurations which had the required asymptotic boundary conditions. And I'm just wondering whether in your problem as well, if you just thought in terms of Chern-Simons formulations for gravity as well as your gauge theories, whether that might just be easier. Because establishing the required asymptotic structures was much easier just in the first order formalism. Saad Schenker and Stanford.
I see. So maybe I should follow their example and then,
In fact, I mean, just to say that we've been discussing with mathematicians, and if you try to do everything in the second order formalism, even in 2D gravity, it's much more complicated. So it turns out,
I see.
So anyway, that's why I just thought I would say that. But Hirosi, just to take this very, very interesting, let's assume that the solid torus with cutout contributes so that you agree with the untwisted non-factorizability, and then you take seriously the other contributions just for a moment with the vortices. Would it be that there is a way to make sense of that in terms of averages, or which would not be your just your CFT averaged, but where you would have these cross terms? Could you add an extra coupling in your CFT and average over that in some way to get these extra terms?
Oh, okay. Yeah, I'm not sure. What kind of additional coupling do you have in mind?
Well, I'm also not sure, but I'm wondering whether an additional sort of randomness in some way, which couples to a operator that generates a twist in the boundary CFT allows for some correlation between Z twisted and Z untwisted.
Yes, but it has to be that this new direction twisted sector has some moduli dependence probably. In order to have some non-factorizable.
Yeah, and then you average over that. Okay.
Right. Yeah, I think so. Yeah.
Okay. Thank you.
Mm-hmm.
Sorry, probably vague question. In yesterday's paper, the authors considered, tried to make some sort of gravity type description of not the ensemble average, but of a single theory.
Yes.
I was wondering whether there's any sense in which your topological gravity coupled to Chern-Simons could also be done for a single modulus.
Given this new development, it's conceivable. It's certainly interesting to think about that. So the mechanism they had was that in addition to this wormhole, they have what they call half wormhole contribution. And what they showed was that if you don't average, then you have contribution both from wormhole and half wormhole, and their joint contribution factorizes. But if you average CFT side, then half wormhole contribution somehow get wiped out, and only wormhole contribution survives, and that gives you non-factorizable contribution. I think that's what they claim to be seeing in the SYK model. And it's possible that something like that happens in Narayan theory too. That would be very, very interesting, I think. So, because in that case, we know much more about CFT, it's solvable. SYK is more difficult. And well, depending on your point of view, I guess. And but then there must be some bulk interpretation of half wormholes that sort of, because if you have fixed Narayan moduli, then CFT amplitude should factorize. So something must cancel the non-factorizable effect of the wormhole, right? I think that's a lesson that I think I was getting from this Stanford paper.
And is there a way of trying to derive this, even approximately some sort of gravity description for a single CFT?
So that's what we are getting at, right? So namely that if we succeed in this program, then for fixed free scalar field theory with fixed coupling, fixed target space, we will have a bulk dual. But bulk dual probably is not just simple Chern-Simons theory with topological gravity. You have to have a mechanism of inducing this half wormhole or something like that, some non-trivial geometry. I don't know what that is.
Right. I was wondering, constructively starting from the field theory, whether one could go to the bulk description, sort of like they could in yesterday's paper.
Right. Yeah. Well, that's what this guy did for SYK. But yeah, I think it's conceivable one can do something like that. Yeah. That'd be very interesting.
Okay. Thank you.
Any more questions? If not, let's thank Hiroshi again for a wonderful talk.
Thank you. Well, thank you for allowing me to speak a little bit longer than expected. It's always nice.